our next topic is hypothesis tests. Hypothesis tests allow us to make this inference from a sample to a population, just like what a confidence interval would do, but in a more formal way to make decisions about a hypothesis. We are going to first begin with what are called two-tail hypothesis tests, and it will be clear after a while why it's called two-tails, or two-tail. Okay, so page 2. First of all, let's just start with a definition of what is a hypothesis. Well, a hypothesis is a statement that something's true. And what we're going to try to use is our sample to make judgments about a hypothesis concerning the population. So we can go back to our light bulbs example that we've seen before. And we're going to use now our confidence interval in a similar manner as before, but now in a more formal way to make a judgment about about a hypothesis. So again, suppose that a company wants to estimate the mean lifetime of its light bulbs, and they hypothesize that their mean lifetime, mu, is equal to 250 hours. How can we check this? Well, we go out and we take a sample, and we calculate the sample mean, we calculate the sample standard deviation, we form the interval, and we get 264 to 334 as we've seen before. So then the question is, well, is mu equal to 250? Well, because the interval is fully above 250, that says then that mu is somewhere between 264 and 334. So yes, so we can reject mu being equal to 250. We do have evidence from our sample that mu does not equal 250. We've made similar statements like this before with confidence intervals, but this is going to help set us up for a more formal way to do this. So also, similar to what we've seen before, suppose we hypothesize instead that mu is equal to 270. Well, in this particular case, 270 is within inside our interval, so mu could be 270, but we don't know. So because of that, we do not reject, those are key words there, do not reject the hypothesis that mu is equal to 270. Notice I do not say that mu is 270. Well, as we can see from this confidence interval, it could be, but then again it might not. So another way to phrase all this then is there's not sufficient evidence. And again, this is a key phrase here that you're going to see me use throughout. From the sample to prove the hypothesized value of mu equal 270 is incorrect. Now let's suppose that we hypothesize that mu is equal to 350. Is this correct? Well, the entire interval now is less than what we hypothesized mu to be. So yes, so not yes. So we do reject that mu is equal to 350. We do have evidence from our sample that hypothesizing that mu is equal to 350 in terms of the mean lifetime of all light bulbs in the population is 350. We do have evidence from our sample, sufficient evidence, to indicate that that statement of hypothesis is actually incorrect. So let's formalize this more. Well, in statistics and used in a wide variety of other places as well, you always have two hypotheses that you're looking at. One's called a null hypothesis, one's called an alternative hypothesis. Either one or the other is true. Our null hypothesis in a symbolic form is denoted by HO, so O in the subscript, colon, mu equal 250. Some people will also write this as H with a subscript 0. Even though that they put a 0 there, most people will still pronounce it as HO. Notice I am not saying ho, I'm saying HO. Our alternative hypothesis then is the opposite of what's in the null hypothesis. And in a formal manner, we denote this by H with a subscript A, colon, mu not equal to 250. Sometimes people will put H with a subscript 1 instead. Again, I'm not going to call this hot. So when we do hypothesis testing, we will always state our null and alternative hypothesis. We won't call them ho and ha. Instead, we will call them HO and HA. Now, there was one of two possible decisions that we were making based upon this sample in this light bulb example. We either rejected HO. This indicates mu is not equal to 250 if we go back to the original hypothesized value of 250. Or we don't reject HO, meaning this indicates that there's not sufficient evidence from the sample to indicate that mu is different from 250. It might be different. It could be 250. Could be 251. But as we solve with that interval, it gives us a range of numbers, and we don't know if it is equal to 250 or not. Now, you're going to see a lot of different phrasing of wording, and wording is very important. Sometimes, unfortunately, you will hear people say accept HO rather than don't reject HO. But that's like saying, okay, what's in HO is true, and that's not the case, as you saw with our confidence interval example. So do not say accept HO. Even you will see some books that will actually put that in there, unfortunately. I will always take off points whenever I see the phrase accept HO. Now, some notes. Now, most often when performing hypothesis tests, you will always put your research hypothesis in HA. And let's think about why. Notice that I was able to actually show through a confidence interval that mu is not equal to 250, or whatever our hypothesized value was for a particular example here. I was actually able to show that indeed there was evidence that HA is true for my sample. However, I was never actually able to show was mu equal to like 250, even if the interval contained 250. And so because of that, in your research, you want to show that your hypothesis for whatever you're doing your research in is true. You always need to put that research hypothesis into HA so that you can show that it is true. And as you will see shortly, we can also assess a certain level of accuracy with it, just like what we saw originally with confidence intervals. Now, in addition to using the phrase don't reject HO when, let's say, mu was in that interval, some people would say fail to reject HO, and that's fine as well. And this is a key point to what I was just saying here, is that we will never actually be able to ever show that indeed, let's say, mu is equal to a particular number. And so that controls how we actually, where we put our research hypothesis. Okay, let's talk about a classic example that pretty much everyone talks about when introducing hypothesis testing. And that involves jury trials, because the decision process associated with jury trials is often very similar to the decision process that we have with doing hypothesis testing. So juries are asked to consider two hypotheses in the U.S. judicial system. HO would be the defendant is innocent. HA is the defendant is guilty. And in our system, the defendant is assumed to be innocent until proven guilty. As you see how we construct some of these different hypothesis test forms, you will see, oh, okay, I see how you're assuming that HO is true. It's a little bit more difficult to see in the confidence interval approach that we just talked about, but in other approaches, you will see, oh, okay, yes, I do see it. And if you don't, of course, you need to ask questions. So in hypothesis testing, we assume HO is true until there is enough evidence to prove otherwise. And so what happens in a jury trial is that the jury listens to the prosecution and the defense to make a judgment. This is just like taking a sample from the population. Now, if there is enough evidence beyond a reasonable doubt to convict, then we would say reject HO, meaning the defendant is guilty. If, though, there is not enough evidence, there is some reasonable doubt, so there's not enough evidence to convict, don't reject HO. The defendant is not guilty. And look at the wording here. This is the way that in jury trials is worded, not guilty. It does not mean the defendant is innocent, though. It just means there wasn't enough evidence beyond a reasonable doubt to convict. I mean, there wasn't enough evidence from the sample to say, for example, maybe the mean was equal to 250 or it wasn't. So, now, whenever we're making a decision regarding reject HO or don't reject HO, based upon our sample, we could make a wrong decision in the end, meaning in reality in the population, maybe we reject HO, but in reality HO was really true. Well, that would be an error. And in statistics, we have a fancy name for it. It's called type 1. Also, we could say don't reject HO, but in reality, we should have, meaning that HA was really true in the population. And again, we have a fancy name for this kind of error, a type 2 error. And so we have type 1 errors and we have type 2 errors. Again, these are errors that base upon our sample. Our sample led us to believe something about the population that was actually incorrect. So let's relate this back to the jury trial example. A type 1 error would be the jury says the defendant is guilty, but the defendant is actually innocent. Now, in the American judicial system, this is a very, very serious error. And we want to avoid this error. We want to control, let's say, the probability that this happens, and we want that probability to be extremely, extremely low. Type 2 error. Jury says the defendant is not guilty, but we should have said the defendant was guilty. So this would be like letting a criminal go free. Now, in our system, we don't want that kind, and in our judicial system, we don't want that kind of error to occur. But we'd be willing to give up making errors like this sometimes in order to prevent this first error from occurring. So, because of how these errors are defined and which one is more important than the other, type 1 is more important than type 2. In hypothesis testing, when we actually do take a sample and get some numerical values and do some calculations, we are going to control the probability of making this type 1 error. In other words, the probability you reject HO, given that HO is true, we're going to control that probability at a level that we'll just generically call alpha. Well, we've seen the letter alpha already with confidence intervals, and guess what? It's basically the same thing. Now you might be wondering, well, geez, you're introducing a lot of terminology here. I got to do that. Some people will use different terminology than others. And so here's an example. Some people will refer to this alpha as the level of significance. And you will see why that occurs because this alpha is going to play a critical role in deciding when we reject and when we don't reject HO. Now, a type 2 error, we are not going to control this error in hypothesis testing, at least not as direct as we are definitely with these type 1 errors. And so, but we can still define it, and we will talk a lot more about type 2 errors outside of these notes. But for now, let's say the probability of type 2 error is going to be defined simply as the Greek letter beta. And so here we have a nice little table that helps describe these kinds of errors that can occur. So for example, if I base upon my sample now, if I reject HO, but in actuality HO was true, there's where my type 1 error would be. But if I rejected HO, and in actuality, in terms of the population, HA is true, good, I made a correct conclusion. And you can look at the correct conclusion in type 2 error cells of the table as well on your own. So on page 7 then, I have then the corresponding probabilities written in the table. And before I forget, I do want to mention this. Very often on a test, I will give a table like this and ask students to simply fill in the blanks, meaning don't give the body of the table and have students write out where type 1, type 2 errors would be, where the correct conclusions would be. Okay, so with respect to these errors here, notice what's in yellow, what's in blue. So probability of a type 1 error is alpha, but notice the probability that you don't reject HO, given HO is really true, is 1 minus alpha. So I use the complement to find that. How did I do that? It goes back to our probability section when we were working with events. And lastly, before we move on to get some numerical examples again, I want to talk about something called power. Power is a probability. Simply the probability you reject HO given that HA is true. So you have made a correct decision. And remember, HA is what contains typically your research hypothesis. So if you're a researcher and you are actually performing an experiment that's going to involve a hypothesis test, you want your power, the probability that you reject HO, given HA is true, you want that to be as large as possible. We will have a subsection later in the notes here that talks about what are called power studies, so that you can investigate how to best do your experiment with a sufficient amount of power to be able to prove your hypothesis to be true. In other words, the alternative hypothesis to be true, given that HA is really true. And so, I guess I've already answered then this question here. Well, you want this probability to be as large as possible. Okay. Next, for the rest of the notes here, we're going to outline 3 different methods to perform a hypothesis test. 1, using a confidence interval, basically using what we just got done doing. 2, using what's called a test statistic. Here you will see why we refer to these as two-tailed tests or two-sided tests. And then also a p-value, which just gives a different way of looking at a test statistic method. So these two methods are very close in similarity to one another. Note that for doing inferences about a population mean, all 3 of these methods will give you exactly the same result in terms of reject HO or don't reject HO. Just how they go about doing it is just a little bit different. Okay, so let's begin with the easiest method. This is the confidence interval method. There are 4 steps. So with each of these hypothesis testing methods, there will be a set of steps. When you do a hypothesis test, like a project or a homework problem or some other graded activity, including a test, I expect you to actually number these steps. I do that because it makes you think in an organized manner. I need to do this, 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 and this in order to complete my hypothesis test. So again, you need to label the steps. If I don't see labels there, unfortunately, I will take off points. Okay, so step 1, state your hypotheses. So the null hypothesis is mu is equal to some number, and as a way to make this very general, how about we just call it mu sub 0. The alternative hypothesis is the exact opposite. Mu does not equal mu 0. Then step 2, we find our confidence interval. Step 3, we make a decision, do we reject or don't reject HO? And simply, How we do that? We check. Is the hypothesized value inside the interval? If it's inside the interval, don't reject HO. If it's outside the interval, reject HO. And then step 4, state your conclusion. And you need to do this in a way that is phrased in terms of the original problem that we're dealing with. In terms of, like, if we're dealing with GPAs, if we're dealing with wind speed, if we're dealing with something else, phrase it in terms of the original problem. Okay, so let's take a look at an example. This deals with GPAs here. And we simply want to test the hypothesis that the mean GPA of all students, doesn't have to be at UNL for a particular university, is 3.0. Now, let's suppose that the probability of type 1 error is alpha. So we're going to do this hypothesis test in a way where we're going to state alpha to be 0.05. We made that decision, and then we go out and take a sample. The sample gave us y bar equal 2.9. Sample size was only 16, and the standard deviation was 0.1 of these GPAs. So, step 1, state your hypotheses. Mu is equal to 3.0 versus mu does not equal 3.0. Step 2, calculate your confidence interval. So, I go through my normal calculations as I've done before, and I get 2.85 to 2.95. Step 3, decide if you reject or don't reject, and you need to tell me why. I reject HO because mu equal 3.0 is not in that interval. Step 4, tell me in terms of the original problem, in terms of the actual data itself, what does this mean? Well, the mean GPA of UNL students is not 3.0. There, we're done. Pretty simple. Just a more formal way of looking at things with a confidence interval. Here are some notes. So the phrasing that I use in step number 4 essentially provides a template for you to use. This is often one of the places where students have problems in terms of wording that correct conclusion in that last step. And so what I've done is I've written out then that phrasing in a way that's more generic here, and then you need to fill in, you need to make it less generic. How about that? That would be a good way to put it. So one way to phrase it, and this is the way I did it, the mean value is different from the value stated in the null hypothesis. Okay? So putting it in terms of the original problem itself, well, the mean GPA is different from the stated value of 3.0 in the null hypothesis. Excuse me. Another way that you commonly see people phrase these conclusions is there is sufficient evidence to prove that mu is different from the value stated in the null hypothesis, where you replace mu here with, let's say, the mean GPA, and then you somehow include, well, what was that null hypothesis, 3.0. A second note. So let's think about what this type 1 error of 5% actually means. The probability of incorrectly rejecting mu equal 3.0 is 5%. Thus, if the whole process of taking a sample, doing the hypothesis test each time was repeated 1,000 times, where the null hypothesis was actually true in the population. That's how, as I mentioned earlier, I said we basically assume the null hypothesis is true first and then do the calculations. Then we would expect, well, 5%, in other words, about 50 times to incorrectly reject mu equal 3.0. This is how this type 1 error, this is how to interpret it. And again, I could ask you on a test, tell me how you would interpret the probability of a type 1 error for a particular problem. This is the way to do it. It doesn't mean that that for this particular hypothesis test that there's a 5% chance that I got it wrong. Rather, what it means is that if you look at the repeated sampling process, again, this goes back to what we saw with confidence intervals, and understanding what a random variable actually means. So this 5% then goes back to the actual sampling process of repeatedly taking samples. On average, we would expect 5% to get it wrong. Okay, let's take a look at another example. So this deals with basically quality control in a manufacturing setting. For some reason, I decided to use volleyballs here, perhaps because I like to play volleyball. I played a lot in my life, and so this is where this example comes from. So one of the leading manufacturers of volleyballs is a company by the name of Mikasa. And let's say that they're concerned whether their volleyballs are being produced with the correct radius of 11.6 centimeters. So what they do is, let's say maybe in their manufacturing plant, they randomly sampled 36 volleyballs that have been produced. And what they got was that the sample mean was 11.5. The standard deviation was 1. Here's part of the data set. So the first volleyball was 11.38 that they got in the sample. The next one was 12.78, and so on. So, given this information then, is there evidence to show that the volleyballs are being made incorrectly? Let's conduct a hypothesis test to check it out. We're going to use a probability of a type 1 error of 0.05. So, let me go over here to R. Okay. So, my data is in volleyball.csv. So, let me go ahead and read that in. Okay. And from that, then, I can find my sample mean using the mean function as we've done before. I can find my sample standard deviation using the SD function as we've done before. I can state my level of alpha. I can find my sample size using the length function as we've done before. Let's go ahead and do that. And now let's actually find the interval using the same kind of code that we've seen before. Notice how I use the QT function to find the corresponding quantile from the t-distribution that we need for the interval. I find the lower bound, I find the upper bound, and I put it all in a nice little data frame to make it look nice. And here's my confidence interval, 11.16 to 11.84 approximately. Let me go back to my notes now. Now, you could also, similar to what we saw with confidence interval section, there's also a function called t-test that will do these calculations for you. Where in our data set itself, there's a variable called radius. The data is in a data frame called volleyball. I state I want a two-sided test. Once we talk about one-sided, two-sided, we talk about another way to do confidence intervals. To do hypothesis tests. That will make sense why I call it two-dot-sided here. But for now, two-sided means exactly the same thing as two-tail. It's just this is the terminology that R uses. Mu is equal to 11.6. That's our hypothesized value. My conf.level is 95%. This is 1 minus our alpha. Again, this is just how R sets it up. It uses slightly different terminology. It just needs some way to get the programming done, and this is what it does. So based upon that, then, here's my confidence interval that I just calculated. So let's do the hypothesis test. I set up my null hypothesis and my alternative hypothesis. Then I do my confidence interval. Here's how you would do essentially the by-hand calculations outside of R. Now, in this particular case, my null hypothesis states a value of 11.6. Notice that 11.6 is within the interval itself, so because of that, I need to say do not reject HO. Or I could say fail to reject HO. I cannot say accept HO. I cannot say, oh yeah, mu is equal to 11.6. I can't say that. So do not reject HO because 11.6 is in the interval. So what does this mean in terms of the original problem? Well, there is not sufficient evidence now to prove from this sample that the volleyballs are being made incorrectly. Another way to say this is that there's not sufficient evidence to conclude the population mean radius is different from 11.6. So again, it could be equal to 11.6, but it could be something else as well. And we can see that from the confidence interval. So phrasing is very important, and this is a place especially where students struggle when they have do not reject HO as the conclusion. You can think of what I have here then as a template that you can use. Just replace the generalities in this phrase with what it means in terms of the original problem, like I had done above. So if you were actually a manufacturer, in this case of volleyballs, well, what should you do? Well, continue with production of the volleyballs. Until your sample tells you something otherwise, then let's keep on going with what we're doing. Another note, notice I did not say, oh, the volleyballs are being produced correctly. I can't say that. And we can see that from the interval itself that while mu could be 11.6, it could be 11.59 as well. So that's why I cannot say that. And this also then corresponds to the probability of a type 2 error that's not being controlled. Okay. So now just as a reminder, you can get this information from t.test and put it into an object itself. So for example, if I say save.results gets the results from t.test, I get what's refers to as a list as a type of object. And if I use names with a list, what will happen is I see all the information that's located inside of it. And I can pull out bits of information from inside of it by using the $sign and whatever is given here in the list. Just a small side note that sometimes you see. I don't know if we'll see it in this class, but you might see it in another class where you use R. Let's say instead, rather than conf.int, it was conf space int as that value there. Now, if you were to put then conf space int after this $sign there, R is going to return an error because it doesn't know how to handle the space. So what one can do instead is actually leave the quotation marks around that and put it right after the $sign. So even what I have here in terms of conf.int, if I were to put the quotation marks around conf.int, I would still get the same results back. Now, R recognizes this conf.int actually as a vector that has two elements in it, so I can pull out individual elements of that vector by using the correct syntax. Okay, so confidence interval method is not too bad. It's very similar to what we did in the confidence interval section. Excuse me. But now we're more formally stating a set of hypotheses to work with. Okay, so next let's talk about the test statistic method to do a hypothesis test. And this takes us to page 14 of the notes. There are 5 steps. First, state your HO and HA just like what we did with the confidence interval method. And then step 2, rather than finding a confidence interval, we're going to find what's called the test statistic, where we find the sample mean, and now we subtract off that hypothesized value. So what this essentially is, when we're forming the statistic then, we're assuming that HO is true by forming this test statistic. And then we divide by S, which is also divided by the square root of N. So in an intuitive sense, what we're doing is we're looking at how far is Y bar from my hypothesized value, my population mean. And from an intuitive sense too, you would think the farther Y bar is from this mu0, the more likely it is that you will reject the hypothesis. Alternatively, if Y bar was exactly equal to mu0, well, would you reject? Well, no, because what you're getting in the sample, the information you get from the sample is essentially exactly what we hypothesized to be in the population. Now we also know that this Y bar is going to vary from one sample to the next. So we need to take that into account. And the way that we do that is to divide by the estimated then standard deviation of y bar, s divided by square root of n. And so by dividing that, then that helps us to take into account, the distance that y bar is from mu 0, how that could simply be due to the variation that that one would expect to observe. Now, this thing is called the test statistic. This should look very similar to what we have seen previously in terms of we worked with random variables, the capital T, a capital Y bar, a capital S. The key is that now we are putting in the hypothesized value of mu 0. In other words, what was in the null hypothesis. And what we also know from earlier is that we can make a corresponding probability statement corresponding to this random variable. And that is with a probability of 1 minus alpha. Notice how alpha is appearing there. This value, this t, should be between a negative value for my t distribution, a positive value for my t distribution, or negative and positive quantile from the t distribution. We have a probability of 1 minus alpha that this is going to occur from one sample to the next. But again, this is assuming that HO is true. Okay? So what this means then is that if we go out and take a sample then and get an observed value of that statistic, we have a general idea where we would expect this statistic to fall within, provided HO is true. And here's a graph of this. Obviously, it's not necessarily drawn to scale. I just simply drew it out. So what we would expect to happen is that a test statistic maybe would fall here, maybe it might fall there, maybe it might fall there relative to the t distribution axis. It might fall there, it might fall there, it might fall there. That would not be unusual to happen with this particular set of assumptions that the null hypothesis is true. But instead, let's say we had a test statistic fall way out there. Well, that area, that part of the t distribution has a small area underneath its curve. It's, in other words, is representing an unlikely region. And so because of that, then that might make you think, something's going on wrong here. I got this particular test statistic, but it falls so far out from the center of the t distribution. Something must be wrong. Maybe my original hypothesis for what mu is equal to in terms of the null hypothesis is actually incorrect. Same thing would occur, let's say, if I'm way out here as well. And so what these quantiles from the t distribution then give you is like the border from what you would expect to happen, meaning in between here, versus what you would not expect to happen if the null hypothesis was true. And so if I do get a value out there, or out there, then, hey, something's wrong. I think my null hypothesis that I'm stating is actually incorrect. So this is the logic of how hypothesis testing works. We assume the null hypothesis is true. We take the sample, and we, based upon our sample, we calculate an observed value of a test statistic. And we check, is this observed value in a region that is reasonable to happen if HO is true? Or is it in a region of the t distribution, does it fall there, where that will be very unlikely to occur if the null hypothesis was true? And if that does, if it does fall in this unlikely area, then let's reject that null hypothesis for what the mean would be. Okay, so you can also see, I don't know why I have a space there, why this is called a two-tailed test, because there are two tails of the distribution where you could actually reject HO in terms of where that observed value of the test statistic falls. Some people will also refer to this as a two-sided distribution. Two-sided test as well. So step 3, state your critical values. That's what I was referring to above. Again, we can use the QT function from R to find these for us. And then step 4, decide if you reject or don't reject. And especially when you're first learning how to do hypothesis tests, it's always helpful to draw out what the t-distribution would look like. It doesn't have to be to scale, but if you draw it out, this will really help you understand how the hypothesis test works. So here's my t-distribution. So I draw the distribution. I plot where the critical values fall. Label the graph with reject or don't reject regions. Plot where the test statistic falls. Well, maybe it might fall, let's say, right there, whatever the numerical value is. And then write reject, don't reject, and provide a reason. So I could say reject H, in this case I would say don't reject HO because the test statistic value T is within inside the two critical values. If instead the test statistic fell out here, I would say reject HO because the observed test statistic value was greater than that upper critical value. Or if, let's say, the test statistic fell right there, I would say reject HO because the test statistic is less than that lower critical value. And then step 5, describe what 4 means in terms of the original problem. Okay, so let's take a look at an example. This goes back to my volleyball example again. So I can state what mu0 would be, 11.6. I find my test statistic value. So I take y bar minus that mu0, and then I divide by s divided by the square root of n. I can find my critical value using the QT function from R as we've done before. Again, remember how the QT function works. We state for the p argument an area to the left of that quantile that I want. In this case, would be 1 minus alpha divided by 2. State my degrees of freedom, which is n minus 1. And then put everything nicely in a data frame. So my test statistic value is negative 0.6. My critical value is 2.03. Note that this is actually going to be a negative and a positive 2.03. So let's go back to the lecture notes. Note that I should also say the t.test function as well actually computes that test statistic value for you automatically. Note it does not give you the critical value though, or critical values. Excuse me. So let's go through the steps. Step 1, state your hypotheses. Step 2, actually do the computation of the test statistic, negative 0.6. Step 3, state your two critical values, a plus and a minus value from the t-distribution, where we have alpha divided by 2 and minus 1. So I get plus or minus 2.03. Step 4, let's graph it out. So I draw my t-distribution. Then I put the critical values on it. Then I plot my test statistic value, negative 0.6. Then I label my don't reject regions and my reject regions. Obviously, negative 0.6 falls in my don't reject regions. So I say, well, because negative 0.6 is between these two critical values, don't reject HO. That's how it's done. But again, let's think about, again, how we're doing this. What these critical values are giving us is a, let's say, a probable region for the test statistic to fall within if the null hypothesis was true. And indeed, negative 0.6 did fall within that region. So that's why we don't reject HO. So step 5, what does this mean in terms of the original problem? Well, there's not sufficient evidence to prove the volleyballs are being made incorrectly, or instead you can word it like this. There's not sufficient evidence to conclude the population mean radius is different from 11.6. Okay, so that takes us to page 18. Note again that we can save the results from the t.test function into an object, and then we can extract important elements from that object. So for example, we have this thing called statistic here. If I extract statistic, that's how I get my negative 0.6 out. Now, to help you understand this test statistic more, or better, I want you to think about what would happen if, let's say, the sample mean changed, but everything else in terms of the numerical values, in terms of like the standard deviation, alpha, the sample size, they all remain exactly the same. So before we had y bar equal to 11.5. Well, let's suppose that y bar was actually 11.6, which is exactly the same as the hypothesized value. Well, when we write our statistic here, we can see what's going to happen to the numerator. It's going to become 0, unless t is equal to 0. And so we're going to be right dead center in that middle of that distribution. And so because of that, we'll say don't reject HO. And again, think of it from an intuitive standpoint. If your sample mean is exactly the same as what you're hypothesizing your population mean to be, is the sample giving you any evidence that the population mean is anything different from 11.6? Well, no, it doesn't. So that's why your test statistic ends up being 0 and you're right in the middle of the distribution. Okay, so when we had y bar equal to 11.5, then we're getting a little bit farther out from the middle of the distribution, and we get a test statistic of negative 0.6. But let's say we go a little bit farther out. Now let's say that y bar is now farther from 11.6, and now it's 11.4. My test statistic is now negative 1.2. I am still within that don't reject region, though. Excuse me. I'm still within there. Given the amount of variability that we have in our data, as measured by s divided by the square root of n, it would not be unusual, with a sample size of 36, to observe a sample mean of 11.4. It would not be unusual. So because of that, I say don't reject HO. But let's go further. Let's say y bar was actually 11.2 instead. Now I'm getting farther out from that center, from that 11.6. Now the t-test statistic is negative 2.4, and look where it falls. And think of, area underneath the curve corresponds to probability. And we can see being this far out in the tail of the distribution is very unlikely to occur if the null hypothesis is true. So because of that, then, I say, I think we should reject HO here. There is sufficient evidence from the sample that indeed we have a problem with the manufacturing of our volleyballs. The mean is not 11.6. Now, to further help you out, I've actually constructed a nice little Excel spreadsheet that, and I want you to investigate this on your own, that allows you to change y bar, and the entire spreadsheet will update itself. Now for now, just focus on the two-tailed test here, and the decision don't reject, and also the plot right below. We'll talk about the other portions of this Excel file later as we go along. But the key is that as I change the sample mean, everything else updates in the plot, in the spreadsheet, and we can see how, in this case, as I go further from the hypothesized value of 11.6, I'm getting more and more and more evidence to say, yeah, there's something going on wrong with our manufacturing. The mean is not 11.6. Now, the spreadsheet is also set up in a way so that you can change your sample size. You can change your standard deviation. You can change your hypothesized value. You can change your alpha. So what I want you to do on your own is set everything to what we originally had with the volleyball problem. Then pick a particular item to change, let's say S. Investigate what happens as you increase S. Investigate what happens as you decrease S. And I want you to relate the reject and don't reject result to what you would expect to happen intuitively for having, in this case, more variability or less variability, but also through looking at the mathematical formula for that t-test statistic. This is a critical aspect for you to understand how hypothesis testing works, rather than thinking, oh, it's just some kind of statistical magic that has been invented. It's not that. There's a good intuitive understanding that you can come up with, and this spreadsheet is going to allow you to do that. So for each of these things in red, look at what happens when you increase it, look what happens when you decrease it, and try to relate this to an intuitive understanding of what is actually occurring with this hypothesis test. Okay. So that takes us to page 21 then. We've talked about some of this stuff, so I'm not going to go over it once again. Let's see now. Let's look at bottom page 21 here. So why did we put our hypotheses like this, where the equal sign was in the null hypothesis, then and you don't see an equal sign at all in the alternative hypothesis? For all hypothesis tests, and you're going to see different hypothesis tests as we go along in our course, we always need to have an equal sign in the null hypothesis. And that has to do with a lot of the mathematical theory that underlines the hypothesis testing process to make this all work out. An intuitive way to think about it is that, you know, when you form your test statistic here, you need to do it in a way that HO is true. And so to do that, that's why you need to always have an equal sign corresponding to that null hypothesis. Now, if some kind of new action is to be taken when a hypothesis is proved to be true, this hypothesis is typically done in HA. And this is because we can control the probability of making an error in our decision. So you should think about it this way. What would happen if Mikasa's volleyballs did not have an average radius of 11.6? Well, production of the volleyballs would be stopped. That's the action. What would happen if Mikasa's volleyballs have an average radius of 11.6? Well, the production of the volleyballs will continue. And so that's how you can think of what goes in the null hypothesis, what goes in the alternative hypothesis. Think of it in terms of the action. I also gave you another example earlier with respect to where your research hypothesis goes. Now note that unfortunately some textbooks use the normal distribution instead of the t-distribution when sample size is greater than or equal to 30 and sigma is known. And we've discussed this before, the problem with doing that, and that is sigma is never known in actual application. So that's why we will always work with the t-distribution version of our hypothesis test here. And similar to how we discussed before, how a confidence interval, even if you don't have the underlying assumptions such as normality, in terms of your y1, y2, y3 have a normal distribution, even if that does not hold exactly, statistical research has shown that the confidence interval still works well in most cases. The same thing happens here with hypothesis tests. So it just is just not worthwhile to go through this other particular case, even though you often see that in books. And again, we will only use the t-distribution if you end up using the normal distribution for a hypothesis test. I will take off points. Okay, so the third of these three different ways to do a hypothesis test is what's called the p-value method. This is very, very similar to the test statistic method. The difference is, instead of looking at values that will be on your x-axis of a drawing of a t-distribution, instead you're going to look at areas underneath the curve, or probabilities, to make the judgment. So if we go back up to where we were before, excuse me while I get back up there. Okay, let me do some erasing too. Okay, so this is a volleyball example again. So we compare negative 0.6 to these two critical values. So comparing numerical values on the x-axis. Instead, what you could do is, let's calculate the area underneath this curve. Okay. That area is obviously bigger than the area to the left of this critical value. So because of that, since this area that we get from our test statistic is bigger, don't reject HO. Okay? If instead, let's say the test statistic was instead, let's say here, oops, let me get my pen back, and we look at the area to the left, we can see that area is a lot smaller than if we would look at the entire area to the left of that critical value. So because of that, since that area is smaller, that means, again, we have an unusual situation occur, so let's reject HO. Now you can make the same statement as well over here. Let's say if my test statistic falls on the right side, I can see my area is very small relative to the same area that we would calculate to the right of that test statistic. The key is that we're looking at probabilities of being extreme relative to the t distribution. And that's how we're going to work with p-values. Or these things that we're going to call p-values, I should say. Okay. So these p-values actually represent probabilities. And that's where the p-value comes from. So step one of the process is that we're going to state our HO and HA. Step two, we're going to find the p-value. And all the p-value is you take the absolute value of what you originally would calculate, let's say with a test statistic, and look at what's the probability that a random variable t would be that extreme. In other words, probability that t is greater than the observed value of your test statistic, the absolute value of that observed value. And we're going to multiply it by 2. So this is very similar to what I just demonstrated in the plot. We're looking at probability of being out on the distribution, far out. And the reason why we work with an absolute value is because, you know, the t distribution is symmetric. So let's just work with positive values always. And we multiply it by 2 because there are two critical values that we're working with. Let's say with the test statistic method. So there's 2 places on that distribution where you can end up rejecting. That's why we multiply by 2. Okay. So how do I find this particular probability in R? Well, let's say I have an object that has my test statistic value in it. It's called t. I use ABS for absolute value. And then I go back to my PT function. Remember what this is going to find. This is going to find the probability that capital T is less than the absolute value of t. If you find areas to the left in terms of what the PT function does. If I actually want an area to the right, as denoted by that greater than sign there, and so I use the complement, and so I work with 1 minus, and then I multiply it by 2. Okay, so here's a plot of basically what we're doing here, and we're just simply trying to find this area right there, and multiply it by 2. Okay. So what is then the p-value giving us? This is on page 24. Well, the p-value is giving us is the probability of finding a value of the observed test statistic at least this great or at least this extreme, assuming the null hypothesis is true. This is the exact same idea as comparing these t computed values to critical values. Again, rather than looking at values that are on my x-axis of my plot, now I'm going to look at areas underneath the curve. That's it. Okay. Now, how else could you find this p-value? Well, you could actually do the formal integration of the t distribution and then multiply it by 2. That's how it would be done. Again, you're not responsible for the calculus aspect of this right here, but I know that some of you have had calculus before, and this is how the actual computation is being done. Okay, so step 2, find the p-value. Step 3, state what your alpha is. This is our type 1 error rate. Remember what that is actually doing. If we come back up here. So, perhaps let's say if I think of it in terms of a critical value, I'm finding a value there. I'm finding a value there as well. And the area in that tail is alpha divided by 2. Okay? Alpha divided by 2 plus alpha divided by 2 is alpha. So underneath this curve, there's an area of alpha where essentially my test statistic could fall in, where I end up rejecting. Then I decide if I reject or don't reject HO. Simply, if the p-value is less than alpha, reject. If the p-value is greater than or equal to alpha, don't reject. That's it. Make sure you understand why we're looking at it compared to alpha, why greater than means don't reject, less than means reject. You may remember me mentioning earlier a phrase, the level of significance. That's another way to phrase what alpha is representing here. And this is why. Alpha is playing a very important role here. It's a significant role that it's playing. And this is the level of it. And just what the name, that's how the name comes about. Step 5, state your conclusion. Describe what 4 means in terms of the original problem. Now, I will tell you that when you're using a computer to do a hypothesis test, very frequently these p-values are given to you automatically when you do the hypothesis test. And so when you're using a computer to do a hypothesis test, very frequently this is the easiest way, the quickest way to get the job done in terms of doing the hypothesis test. Okay, so let's take a look at how we would do this in R then. Let's see here. So to compute then the p-value, so again we have t is negative 0.6. We're going to find the probability to the left of the absolute value of 0.6, which is 0.728. I do 1 minus it, do the complement, I get 0.27, and then I'm going to multiply it by 2 because I can reject both on the left side and the right side of the t distribution and get a p-value of 0.55. Also, from using the t.test function, notice it actually gives you a p-value of 0.55 as well. So putting this all together then, I can go through my steps of doing my hypothesis test with a p-value. State your hypotheses, find your test statistic, find the corresponding p-value of 0.55. So again, what does this mean? The probability of observing a test statistic this great in magnitude is 0.55 if the null hypothesis was actually true. Therefore, then, this is a likely thing to happen. A probability of 0.55, that says, yeah, that's reasonable to have happen in actuality. So because of that, then I'm going to end up saying don't reject HO. So step 3, state your alpha. Step 4, p-value greater than alpha, therefore do not reject HO. And so here's an actual diagram of this. And this diagram actually corresponds to what I was demonstrating towards the beginning of this p-value section. We are comparing how far out this observed test statistic is relative to the distribution. And to do that, we could find the area to the right of this value. That area is 0.2762. And if we wanted to, we could have actually just compared to alpha divided by 2, 0.025, and had exactly the same conclusion. In standard practice, though, people will always multiply this by 2, multiply that by 2, so that you can compare directly to alpha itself. So step 5, what does this mean in terms of the original problem? Well, the sample does not provide enough evidence to suggest that the volleyballs are being made with the wrong radius. Okay, So on your own, I want you to do this. Find what the p-values would be using R for these 5 cases there. Also, on your own, I want you to go back to this Excel file that we had. Oops, for some reason it went to a different screen. Let me bring it back over here. I want you to use this Excel file and take a look at the p-value every time that you change one of these values, one of these numerical values in red here. Look at the p-value, see how that affects things. Again, that's so that you get a better understanding of what hypothesis testing is doing. Okay, so just to conclude here, an understanding of what this type 1 error rate actually means, type 1 error probability. Please read this on your own. Again, I could ask you a question on a test for you to tell me what it means as well. This is very important. One point of emphasis that I want to make is that for doing one hypothesis test, it does not mean your chance of an error is like 5%. Rather, what this is doing is looking at, if you were to repeat the sampling process over and over again, what would happen on average if the null hypothesis is true. Okay, so with that then, that concludes then this part of the hypothesis testing notes.